Now, different waves have different properties. There are 4 basic properties that you can use to characterize a wave. They are amplitude, speed, wavelength, and frequency. Now in this video I just want to talk about the first 2, amplitude and speed. We already mentioned in the last video what amplitude was. Here we've got a wave. Here's where you would be if there was no wave. So if this is a water wave, that would be the water level. The amplitude is the peak height. It's the height of the peak above where the baseline for the wave is. So where my little arrow there is the amplitude. Now, it's related to how much energy that the wave is carrying. And in fact, the energy that the wave is carrying is proportional to the amplitude squared. Now, we're not going to do any math with that, but it's kind of an important thing to know. Because what happens if you double the amplitude? If I double this, say the amplitude was A before. I can write a proportionality like a little equation. Here's the energy. I'm going to call it E. And if I say proportional to, I can say it's equal to some constant. I don't know what that constant is. But it's equal to some constant times the amplitude squared. So I've written a little equation out of this, what I've said in English up here. Now, here's the important thing about that. What happens if I double the amplitude? If I were to double the amplitude, that's like where every place I see an A up here, I put a 2A. So I'm replacing A with 2A if I doubled the amplitude. What's going to happen to the energy? Well, if I take the parentheses off here, it's 2 squared is 4. So the new energy is going to be, this is the original energy. The new energy will be 4 times the old energy. So here's the important thing about that. If you doubled the height of the peak, that's going to quadruple the energy that the wave is carrying. Now imagine this wave is an earthquake wave moving through the earth. A very small change in the amplitude of the wave is going to result in a tremendous change in the energy that that wave is going to be carrying. Same thing with an ocean wave. If you've got a small change, relatively small change in the height of a wave, it can lead to a larger change in the energy. So energy of the wave is related to the amplitude. If something is acting like a wave, you can look at the amplitude and you can figure out what its energy ought to be. Now, there's a related concept called intensity. Intensity is the energy that the wave carries. Per second, per square meter, say. So what would be the SI units of this? The SI units of energy we said were joules before, way back in Module 1. So if you look at how much energy this wave is going to hit something with, how much work it's going to be able to do every second per square meter that it hits, that's the intensity. And the intensity is proportional to the energy. So here's the energy right there. So if you doubled the energy, it'd be doubling the intensity. Now when we're talking about an electromagnetic wave, like light, what we're talking about is intensity is brightness. So when you have brighter light, that's more intense light. And that is related to the energy that the wave is carrying, and that is related to the amplitude squared. So you can talk about more intense light, brighter light, or less intense light in terms of how much energy you're getting per square meter that the light is shining on. All right, what about speed? This wave is also moving. This is a snapshot in time. If I looked at it the next instant in time, the whole thing would be shifted over by some amount. The speed doesn't depend on the amplitude. So however high you make the peaks or low, that doesn't really affect that doesn't affect how fast the wave is moving at. Those two things are kind of independent of each other. They are independent of each other. So if you've got a tsunami moving across the ocean, that's going to be moving at pretty much the same speed as an ordinary ocean wave. What does matter is the speed of a wave is affected by the medium. That is what it's moving through. Things will move at different speeds. Waves will move at different speeds through different media. Now, light moves at the speed of light, which you were looking at in a previous assignment. Something like 2.9979 times 10 to the 8 meters per second. That's the speed of light in a vacuum. And light will move at a slightly slower speed when it's moving through air, and at a different speed than that when it's moving through water. So the speed of light gets affected by what medium it's moving through. It's moving at this speed through a vacuum. So we should always say the speed of light in a vacuum is this. Now, if you have different kinds of waves, the electromagnetic waves all move at that same speed. But you can have different kinds of waves that move at different speeds, like sound waves. If you have a sound wave moving through air, it moves around 330 meters per second, roughly. It depends on the temperature and the air pressure and some other stuff, exactly what that number is, but it's right around there. So you can see sound moves a lot more slowly than light does. And the speed of sound in different gases will be different. Speed of sound in air is one thing. Speed of sound in water is another. Speed of sound in helium would be another thing. You may have noticed that when people breathe in helium, their voice gets really high and squeaky. It changes the pitch of their voice, makes it higher. If you breathe in a heavier gas than air, like sulfur hexafluoride, it will cause your voice to go down really deep. And all of this is because in different media, in different gases, the speed of sound will be different. That will change the pitch of sounds that are heard in that medium as well.